Let's write down a formula for the average kinetic energy of one gas molecule. So we know the formula for kinetic energy, and it's 1/2 mv squared. Okay, so let's take one gas molecule. So that's going to be, this mass is going to be the mass of that molecule. And then we want the average velocity. So let's go ahead and mark a little bar on top of that V there. So that'll indicate average kinetic energy of one gas molecule. Of mass m. There we go. So that's what that is. Now here's the cool and amazing and wonderful bit is we can write an equal sign here and put a 3/2 kT. And if you think about it, it's a little mind-blowing. So this is temperature that we've defined by having thermometers, and then we just did that little tweak where we put it on the absolute Kelvin scale. And this is Boltzmann's constant again. And basically, it's a constant, and 3/2 is a constant. So basically, we're saying that kinetic energy equals temperature. Isn't that fun? It's amazing. So, so the so the motions of ideal gas particles are what we measure as temperature. So when we say that we measure molecular motions, we're definitely doing it with this concept of temperature. So that's pretty cool. So sometimes we'll take this and we'll generalize it just a little bit. We'll call it thermal energy. So thermal energy is the kinetic energy of internal molecular motions. And that's true in gases, liquids, and solids. So as those little guys are jiggling around and doing their atomic dances, that the energy contained in that dance is called thermal energy. You can solve this if you want to. So if we multiply both sides by 2, the 2's go away down there, and we can just write an expression for the average velocity, and that's root 3 kT over the mass of our molecule. And that's pretty cool. Sometimes we'll call this, to be careful, we'll call this the root mean squared velocity. And that pops up so often we even give it an abbreviation, root mean squared velocity. Because what did we do? We squared it, then we took the average, and then we took the square root. And so those three things are encapsulated here. All right, what's this thing I drew down here? It turns out that the average velocity is indeed, or the root mean squared velocity, is not the only velocity that is present. So I forgot the label here. This is on the x-axis. It is velocity with a V, and it's in meters per second, and it's approximately right for oxygen molecules at room temperature. So this is about the curve you get, and so really fast ones are moving in excess of 1,000 meters per second, and then we've got a peak somewhere in the 400, 500 meters per second range, and then we've got kind of a power law drop off, and there are a few that are moving very, very slowly as well. So that's happening right now, right around us. That's the velocity distribution of these molecules. Just wanted to make a point that the RMS velocity isn't where you might guess. So this is not a symmetric curve. Beyond my bad drawing skills, this is pretty steep on the low velocity side, and then there's this kind of a long tail on the high velocity side. So there are different shapes on either side. You might say the average should be right around here, but if we do this computation here, the root mean squared velocity ends up, I missed. It's lower than that, but whatever. My line will stand. So this is VRMS down here. This is the V bar we calculate from this formula is kind of skewed to the high side because we've kind of done an average where we're weighting by v squared rather than just velocity. So the VMRM is a little bit skewed from the peak here. It's of no concern. It really is the average kinetic energy, and it's just that those guys weigh a lot, so they're pretty potent out there. This is interesting too when you're considering the evolution of planetary atmospheres, just as an aside here, because these very high velocity molecules, if they happen to be also very high in the atmosphere, that is a high velocity and it may risk exceeding the escape velocity of the planet. So especially planets that are small in size and don't have a big escape velocity, they can lose their atmospheres because over time, because molecule by molecule, those gas particles will exceed the escape velocity of the planet. They'll leave, they'll never come back. So planets like the Earth and Venus cannot hold on to their hydrogen and helium, but they can hold on to their oxygen and nitrogen. So that explains why hydrogen and helium are basically non-existent in the atmosphere of Earth.